let's continue in going back 2.3 functions and relations. So going back to these questions, another way to determine if these graphs are functions is by using the vertical line test. So the vertical line test says, let's go back down here. If a vertical line crosses a graph more than once, then it is not a function. Or you can say it in the positive sense, if every vertical line crosses a graph only once, then it is a function. So you literally can just take a vertical line in your head or look at it. I'll show you on here. You take a vertical line like this, and we will move that around. Okay, so you take the vertical line, you can see that here it crosses it more than once, right there at C and D, or at B, right? And there's a bunch of lines that cross it more than once. All it takes is one, okay? And here, it only crosses the graph once. So every vertical line only crosses in one place. So it's a function. Same thing down here. You can see that all of these vertical lines cross more than once. So it's not a function. And this one, if you go across, this vertical line only going to cross in one place. So that's how you can test it using the vertical line test. Okay. So if you have the graph, that's a simple way to tell if it's a function, visually speaking. Okay, let's continue. Some actual questions. Determine the domain and range of a function. So here's some examples, and we'll talk about actual functions and what they do, what they look like. So find, this is the general idea here, is find the domain and range of functions. We will focus right now on the domain. That's the section. Let's just focus on domain for now, and we'll talk about range later. So first we'll start off with an example before I define what we do. And this one just says find the domain of the function and the function is given f of x equal to x plus 6 over x minus 2. And so this one I wanted to start here because I want to talk about this function. So when we look at this function, what do we have to be careful of for this is a rational function. It's got a numerator and a denominator, so here and here. And so your numerator can be anything, any values up here, but what can we not have in a denominator? What's the concern? So the concern is basically denominator, so like the bottom, right? The denominator may not ever be 0. So this whole thing down here is the question. Like that can never be 0. Now, what value of x would make that 0? So which you probably have the answer, but basically x minus 2 cannot be 0. So x cannot be 2. So in words, you would say the domain is every value, every real number except 2. You can't have 2. So if you think about like a number line, what would that look like? Basically, you'd go to 2, and it would be a hole in the, like a hole like that, be like nothing there. And so you'd go all of these values, but not at 2. So that's how you describe domain. This is your reals. And so the different ways to define or write, not define, but write that set. So another key thing about a domain, if you go back all the way back to the first couple sections here, a domain is a set. Okay, so it's the set of values except 2. So it's all real numbers except 2. So you have to write that in set notation. So we say D is equal to, this is one way to do it. This is set builder notation. This is what we just, it's in that, what we did in the beginning of the class or the videos, the first one. It's X such that, so one way to say it is like this. It's X in the reals, and then the rest has to follow. So you say such that vertical line, X cannot be 2. That's the simple way of using set builder. Using interval notation, you have to do the parentheses, all of this, and then you union the rest of it, and you basically bounce around 2. It's kind of silly notation, frankly, but you go negative infinity up to 2, but you don't include it, so you put a parenthesis. Union, not including 2, and then you approach infinity, like that. So this notation means the same thing. Okay, so in words, we would say the domain is the set of all real numbers except 2. Okay, so that's the wording we would use. And frankly, if you can write that out, I'll be happy with that, because you're describing exactly what it is. All right, so let's actually define domain of a function. How would you find it? What are you looking for? So this is what you do. This is how you think about it. So the domain of a function is the set of real numbers. So is the set of real numbers that when substituted, so that when, like, you plug it in, that when substituted into the function, and evaluated, the result is a real number. The result is a real number. So what we haven't talked about, and it's actually a prereq concept, are imaginary numbers. We will get to a little bit, but imaginary numbers would not be part of a domain. So if you evaluate and you get a negative in the square root, so like that, that's I. Okay, that's not real. So basically it's not real or undefined. That's basically it. And we'll look at the different examples. Okay, so we'll come back to that. So that's what we're looking for. We want to be able to evaluate and get a real number. One way to write it, and here's another domain concept. So domain is equal to the set X, so all values X, such that X is real, and once you evaluate f of X is also real. So this is what I mean by evaluate. Once you evaluate that, it must be a real number. It cannot be undefined and it cannot be imaginary. So if you're a little shaky on imaginary stuff, make sure you look that up in chapter 1. Okay. Or if this is general, just look it up online some more. So let's look at an example, another example. We'll look at a couple. So another example, find the domain, find the domain of f of x equal to the square root of x plus 3. All right, so this is the case. So think about this. We have the square root. What do we must have happen underneath the square root? This is the radicand. So the radicand, what has to be true of this? Okay, so what you say is what's inside the radical. You say x plus 3 needs to be greater than or equal to 0. So you can have it be 0 because the square root of 0 is equal to 0 since 0 squared is equal to 0. So that's all okay. But you must have it be positive as well. So it's non-negative essentially is what you're saying. And then you evaluate this, you solve it. So that's equivalent to if and only if x is greater than or equal to negative 3. Just subtracting 3 on both sides. And so if you're asked to graph that, be able to do that. So you would graph it like this. You go to negative 3 here, and you include it. So you would say, yes, you include it. And you approach infinity like that. So the domain is equal to including negative 3, and then you approach infinity. So that's pretty easy to write. Or you may write it with set builder notation. The set x such that x is greater than or equal to negative 3. Either way is fine when you do that. Okay, let's try another one. So next example. So find the domain. So find the domain of h of x equal to x over x squared minus 9. All right, now there's a couple ways of thinking about this one, but one thing I want to point out on this one is a squared minus b squared and how that factors. That's a typical binomial, right? These are nomials, so binomial, 2 of them. And that always factors to a plus b, a minus b. And so that is what we're going to use, how you can factor it. So you don't want to lose a term in there. You want to make sure you get every value of x that would make that a problem. So now this is a denominator. So this is a radical. We want that to be positive. This is another denominator one. So what must happen or not happen for the x squared minus 9? So basically we say x squared minus 9 cannot be 0. So same thing, and then you got to solve that. So when you solve that, you factor it. It's x plus 3x minus 3 cannot be 0. So in other words, we say x cannot be plus or minus 3. So it's all real numbers except plus and minus 3. So the domain, again, a couple ways of writing it. Try it. Okay. Pause and try this. Is you can say it in set builder, x such that x does not equal plus or minus 3. Or you can basically bounce around negative 3 and 3. It would be negative infinity to negative 3, union, negative 3 to 3, union, 3, and then approach infinity. A real silly way of writing it is this. This is interval notation. The book could ask for that, but this is much better to write. So you want to be able to bounce back and forth between interval and set builder when you do these. Just for sake of discussion too, the graph of this thing, let's just do it right here. The graph of this thing would be basically just bouncing around 3, or negative 3 and 3 like this, and everything in between. So you could have, let's just pick a different color here. And you would have all of these values here, all of these values, all of these values. And then you not include the 3 and negative 3. So, okay, so a couple more to try. Let's do another one. So next example, find the domain. So find the domain of f of x equal to x plus 2 over x squared minus 3x minus 28. Okay, so try that one. And I'll give you another one to try. Try this one. Find the domain. H of x equal to the square root of 16 minus x. Okay, so try both of these, but what would you do for each one of these? Basically, same idea. It's all we have is that this can't be 0, right? Denominator non-zero, and for radical, this has to be positive. Okay, so you have to, and then you just solve those. So same idea. So you have x squared minus 3x minus 28 cannot equal 0, and so to solve that, it's basically you're setting equal to 0 and solving. So you factor this thing. You can say not equal to is fine. And you want a product that's 28 and a difference that's 3. So x and x. And then what times what is 28? 4 and 7, and the difference is 3. So you want this one to be larger negative, this one's positive. So x can't be negative 4 and positive 7. But you don't stop here. Now you have to write it in a set notation. So the domain is the set x such that x does not equal negative 4 and 7. Or you can write it in that silly notation we did here. Or if the book asks you to do it, you can bounce around 4 and 7. Now this one, same idea, 16 minus x needs to be greater than or equal to 0. And so you say 16 is greater than or equal to x, or you can flip it. X is less than or equal to 16. So this, again, I just add x on both sides, and then you can flip the entire inequality and get it like that. And so we would say the domain is equal to the set x such that x is less than or equal to 16. You can graph it, and you just label 16. You include it, so you put a dot, and it's less than. So let's change colors here. Yellow, like that. Then you go to the left. So that's another way of doing it. Now, just a little side note here. If I did something like this and I said like g of x and I divided by that whole thing, what changes? So what if I did this? Then what changes when I do that? Well, only one thing changes. What is it? Anybody know? Well, the only thing that changes is you say 16 minus x and you say is strictly greater than 0 because it cannot be 0 now. How come? Because it's in the denominator. So then when you solve, you get the same thing as I was going to write this as well in a interval. So it's negative infinity to 16 and you include it. In this case, the domain would be negative infinity, and then what would you do? So yes, you go up to 16, but you cannot include it when it's in a denominator like this. Okay, so that's all we got right now. Denominator can't be 0. Inside the radical needs to be positive or non-negative technically. Okay, probably a few more examples to do on that that are assigned. Otherwise, that's most of the content for that section.